So I had this kind of surreal moment the other night.
Oh, yeah. What happened?
Yeah, so I was driving alone, way out in the middle of nowhere, pitch
Mhm.
black outside, just the headlights on the asphalt.
Right.
And I'm scanning through the radio because I'm losing reception, just getting static. And then suddenly, and I mean crystal clear, I pick up a baseball game,
A live
a
game.
live game.
Mm.
And I realized a few minutes later, listening to the announcer, that the broadcast was coming from a stadium 3 states away.
Wow.
Right.
Yeah.
But here is the kicker. At that exact same moment, my phone buzzes with a text message, and my GPS screen lights up to tell me I have a turn coming up in 200 meters.
It's just a total convergence point.
Exactly.
I mean, you're sitting in this metal box moving at 70 miles an hour, and you're effectively navigating through this invisible soup of information.
That is exactly how it felt. I looked around at the dark, empty road, and I just thought, if I could actually see all this electromagnetic activity right now, if my eyes were attuned to radio waves and microwaves instead of just visible light, this wouldn't be a dark road at all.
Oh, it would be blinding.
Blinding.
We would look like an absolutely chaotic light show. You'd have these massive rolling waves coming from the radio tower, and then sharp, piercing beams from the GPS satellites overhead,
Yeah.
and then just this pulsating sphere of data wrapped right around your phone. We talk about the cloud or wireless like it's, I don't know, magic.
Right, like it's just a given.
But it's really just heavy-duty physics happening entirely in the invisible spectrum.
And that, for everyone listening, is exactly what we're digging into today. Welcome to today's deep dive. We are peeling back the layer of magic to look at the actual machinery underneath.
It's a fascinating topic.
It is. And we've got a massive stack of source material here on the physics of waves. Now, I know hearing the word physics might trigger some high school trauma for you listening.
Oh, absolutely. People hear physics and they think of chalkboards and endless math.
Right, the equations.
But we can leave the chalkboard behind today. The goal here isn't to solve equations. It's really to understand the infrastructure of modern life.
The invisible highway.
Exactly. When you really look at the source material we have, it breaks down perfectly into 3 distinct pillars.
Okay.
You have the how, which is how we actually manipulate energy to carry a message. You have the where, which is the electromagnetic spectrum, essentially the highway these signals travel on.
The real estate.
The real estate, yeah. And finally, you have the code.
The code.
Right, the difference between the old school analog world and the digital pulse that basically runs the internet today.
Okay, I love that structure. Let's start with the how, because the notes here highlight something called modulation. And basically, if I have a radio wave, it's just a carrier, right? It's like a blank sheet of paper.
That's a great analogy.
To send a message, I actually have to write on it. I have to change it somehow.
Right, a pure radio wave doesn't convey anything other than the fact that it exists. So to transmit information, whether that's a voice, a song, or a text, we have to change the wave. We have to modulate it.
Modulate it.
Yes. And according to the physics in our source material, there are really only 3 main knobs we can turn to do that: amplitude, frequency, and phase.
Okay, let's tackle amplitude first. Because in my head, amplitude is just volume, like on a stereo. I turn the knob up, the wave gets bigger, the sound gets louder.
In sound waves, yes, that is the exact correlation. But in radio physics, amplitude is literally the physical height of the radio wave.
The height?
Yes, the distance from the peak down to the trough. The higher the wave, the more energy it's carrying. And this gives us the absolute grandfather of broadcasting.
AM radio.
AM radio, amplitude modulation.
Okay, so to send that baseball game I heard, the station is taking a steady carrier wave and just spiking the height up and down to match the pitch of the announcer's voice.
You're essentially sculpting the silhouette of the wave.
I like that visual.
Right, so when the announcer yells home run, the wave height spikes way up. When there is silence on the field, it flattens out. The radio in your car just traces that outline and turns it back into sound.
But here's the part that I found so wild in the research. AM radio feels like ancient technology.
Very old school.
Yet it has this specific superpower that modern tech, like my brand new 5G phone, cannot touch. It's the reason I could hear that game from 3 states away.
Ah, the ionosphere bounce.
Yes. The notes talk about its interaction with the ionosphere. Can you explain that?
This is called skywave propagation, and it is honestly one of the coolest accidents of nature.
Accident of nature.
Yeah. So the ionosphere is this layer of charged particles really high up in the atmosphere, and it's created by the sun's radiation.
Okay.
Now, here's the nuance the research points out. During the day, the sun is just blasting the ionosphere, making the lower layers, specifically the D layer, very thick and
It's
dense.
blocking things.
It becomes like a sponge. It actually absorbs AM radio waves.
Oh, so during the day, the signal goes up into the sky and just dies.
Right, it gets soaked up. But at night, and this is what happened to you on your drive, the sun goes down. That absorbing D layer dissipates completely, and you are left with the higher F layers.
And what do they do?
These layers act exactly like a mirror to AM frequencies. So the signal shoots up from a tower in Chicago, hits the ionosphere, and literally bounces back down to Earth in Tennessee.
It skips over the curvature of the planet.
It literally skips. That explains why your AM dial goes wild at night and you hear stations from nowhere.
That is fascinating. But we all know the downside to AM radio. It sounds really crunchy.
It sounds crunchy specifically because of that modulation method.
Because it's changing the height.
Exactly.
Huh.
Since AM relies on changing the height of the wave to send data, any other sorts of ambient energy out there just looks like part of the signal.
Like interference.
Right. Lightning, power lines, even the spark plugs firing in your car's engine, they all create bursts of amplitude.
So the radio picks them up.
Your radio receiver cannot tell the difference between the random pop of a lightning strike and the pop of a snare drum in a song. It just plays both.
It's totally susceptible to noise, which leads us perfectly to the second knob we can turn. Frequency.
Frequency modulation, FM radio.
Okay, so if AM is height, what is FM?
With FM, instead of changing how tall the wave is, we keep the height completely constant. It never changes. Instead, we change how fast it vibrates.
How fast?
Right. We squish the waves together, or we stretch them further apart to encode the sound.
Okay, so if AM is a wave getting taller and shorter, FM is like an accordion being squeezed and pulled.
That is the perfect visual. And because the height never changes, all that amplitude noise we talked about, the static from lightning or power lines, it's completely ignored by the FM receiver.
Because the receiver is only looking for the squeezing and pulling.
Exactly. It slices right through the static. That is why FM sounds so much cleaner and clearer than AM.
But there is a massive trade-off, isn't there? The notes mention a specific case study from the sources about Norway, specifically regarding the P3 station on 99.3 megahertz.
Yeah, Norway is highly mountainous, and apparently that is a nightmare for FM signals.
Why is that?
Well, physics is always a game of trade-offs. FM waves are much shorter and much higher frequency than AM waves.
Okay.
So they do not bounce off the ionosphere at all. They are too small and energetic, so they just punch right through it and go off into space.
So no nighttime bouncing.
No bouncing. And because they travel in straight lines and are shorter, they are very easily blocked by physical obstacles.
So it's basically line of sight.
Strictly line of sight. The sources show that if you drive behind a mountain in Norway, or even just a large concrete building in a major city, that FM signal is gone.
Because it can't wrap around the building.
Right. It doesn't have the wavelength to wrap around obstacles the way the big, lazy AM waves do. It's limited to maybe 50 to 100 kilometers tops.
Okay, so we have height for AM and speed for frequency. But the third knob is the one that really powers the entire modern world, phase.
The shift keying.
The source material says this is the basis for Wi-Fi and 5G, but honestly, phase is by far the hardest one to visualize.
It definitely is, but it's also the most ingenious. So think of a wave as a continuous cycle, like a clock hand going around a clock face.
Okay, I'm picturing a clock.
12 o'clock, 3, 6, 9, and back to 12. That is one complete cycle of a wave.
I'm with you.
Phase is simply asking, where is the hand starting?
Where it starts.
Right. If two signals start at 12 o'clock at the exact same time, they are in phase. But if I send a signal that starts at 3 o'clock while the other one is at 12, I have shifted the phase by 90 degrees.
And that shift just starting at a different time that represents data.
Exactly. I can program the receiver to say, if the wave starts at 12, read that as a 0. If it starts at 6, read that as a 1. That is phase shift keying, or PSK.
But wait, the notes mention something way more advanced called QAM, quadrature amplitude modulation. It says this is how we get incredibly high data speeds. It sounds like we're doing a lot more than just sending ones and zeros.
We are. This is where modern engineering gets truly wild. With QAM, we manipulate the phase, the timing we just talked about, Andy, the amplitude, the height at the exact same time.
All at once.
Both at once. Imagine a target board. By changing the phase and the height simultaneously, I can hit a very specific spot on that target.
Okay.
We can define 16 different spots, or 64, or even 256 spots on that one target.
Oh, wow. So one single wave cycle isn't just carrying a simple, yes or no anymore.
Exactly. It's carrying a complex symbol that represents a whole chunk of binary data. We are packing the suitcase as tightly as physics allows.
So instead of sending 1 bit per wave, we're sending 4, 6, or 8 bits.
Yes, that density is the only reason you can stream a 4K movie to your phone over the air. We aren't just wiggling a rope up and down anymore. We are performing a complex microscopic gymnastic routine with it, millions of times a second.
That is mind-blowing when you put it like that. Okay, so that makes the how click for me. AM is simple and bouncy, FM is clear but short range, and phase with QAM is incredibly dense and high speed.
Perfectly summarized.
So now let's talk about the where, because all of these modulated waves, they have to live somewhere on the electromagnetic spectrum.
Yes, they do. I like to think of the spectrum as the real estate of the universe.
Real estate.
Yeah, it's a continuum.
Right.
On the left side, you have the low-rent district. These are long, lazy waves, low frequency. And on the right side, you have the high-rent, high-energy district.
And different technologies basically have to buy property in different neighborhoods based on what they actually need to do.
Precisely.
So let's start over in the low-frequency neighborhood. Radio waves. The source says these are the longest waves.
Yes, the wavelengths here can be massive. We are talking kilometers long from peak to peak. And because they are so physically large, they are incredibly non-intrusive.
Meaning what?
Meaning they pass straight through walls, trees, and people like ghosts. They barely interact with matter.
Which perfectly explains why my car radio still works inside a concrete parking garage. Or why emergency services use these specific frequencies.
Right. If you are a firefighter inside a burning, reinforced concrete building, you cannot rely on a delicate, high-frequency signal. It'll just bounce off. You need a wave that punches right through the concrete.
You need the sledgehammer of low-frequency radio.
Exactly.
But as we move up the street on the spectrum, the waves get shorter, and we hit the microwave neighborhood. Now, I feel like microwave is a really confusing term for most people, because I immediately think of heating up yesterday's leftovers.
Naturally.
But the research says we are actually talking about Wi-Fi and GPS here.
It is the exact same wave.
Right.
Yes. A microwave oven in your kitchen works because 2.45 gigahertz happens to be the resonant frequency of water molecules.
Okay.
So the wave hits the water in your food and it shakes the molecules until they get hot. That's how it cooks. Yeah. But that exact same frequency band, around 2.4 gigahertz, is what is used for your home Wi-Fi router.
Which explains a lot about signal dropouts. The notes here actually break down the difference between 2.4 gigahertz and 5 gigahertz Wi-Fi in your house.
This is a classic everyday physics trade-off that everyone deals with. 2.4 gigahertz is a slightly longer wave. It's more bassy.
Bassy, okay.
So it can travel through your drywall, through the floor, and cover the whole house. 5 gigahertz is a shorter, much tighter wave.
Which means it carries more data.
Way more data. It is much faster. But because it's tighter, it struggles to get through even a single wall.
So if I'm gaming in the same room as the router, I want 5 gigahertz for the speed. But if I'm out in the yard, I need 2.4 gigahertz just to get the range.
You've got it. And this interaction with physical matter is exactly why rain is the absolute enemy of high-frequency signals.
Oh, like satellite TV.
Yes. If you have ever lost your satellite TV connection during a bad storm, it is because the physical rain droplets in the air are literally absorbing the microwave signals before they reach your dish.
That makes perfect sense now. Speaking of satellites, let's look at GPS. Because the research on this is just staggering. I think most of us listening completely take for granted that our phone just knows where we are on the planet at all times.
Oh, we completely take it for granted. The physics making it happen is mind-bending.
The sources say the GPS satellites are 20,000 kilometers up.
Yeah, roughly 20,000 kilometers in orbit. And the wildest part, they aren't scanning the ground to find you.
Wait, what do you mean? What are they doing up there?
They are essentially just shouting the time.
The time. Like a clock.
Exactly like a clock.
Yeah.
GPS is entirely based on time. The satellite sends down a microwave signal that basically says, I sent this message at precisely 12 o'clock and 0.00 seconds.
Okay.
Your phone receives that signal a tiny fraction of a second later. And because the speed of light is a constant, your phone can do the math.
Oh, I see.
It calculates, okay, the signal took 0.06 seconds to get here from space, so that means the satellite must be exactly this far away.
But to do that accurately, that requires incredible precision.
It requires synchronized atomic clocks on the satellites. If the clock on that satellite was off by just 1 microsecond,
1/1,000,000th of a second.
1 millionth of a second, if it's off by that much, your location on the map would be off by 300 meters.
You would literally be driving in the river on your map.
Exactly. The precision is terrifyingly impressive.
It really is. Okay, so moving further up the spectrum from microwaves, we get to infrared, which literally translates to below red.
Right, below visible red light. We mostly experience this as heat. If you feel warmth radiating from a campfire, you are physically detecting infrared radiation with your skin.
But because the wavelength is getting shorter now, closer to visible light, it starts behaving more like light, right?
Exactly. It bounces off mirrors perfectly, but it gets completely blocked by solid walls.
Hence why I have to point the remote directly at the television to change the channel.
Yes, that's an infrared pulse.
But the real killer app for infrared, mentioned in the deep dive sources here, is fiber optics.
The absolute backbone of the global internet.
Right. I always pictured big electrical cables under the ocean, but we aren't sending electricity through those, are we?
No, not at all. We are sending millions of tiny pulses of infrared light through glass tubes.
And how does the light just stay inside the cable if it's traveling across the ocean floor? Why doesn't it just leak out?
Because of a phenomenon called total internal reflection. The glass inside the fiber optic cable acts like a perfect mirror tunnel.
A mirror tunnel.
The light shoots in, hits the side wall of the glass, bounces forward, hits the other side, and bounces forward again. It can travel for miles and miles without losing any real intensity.
It is literally light-speed data transmission.
Exactly.
Which brings us to the part of the spectrum that we actually notice day to day, visible light. And the research really emphasizes just how tiny this slice of the spectrum is.
Oh, it's humbling. It is less than a fraction of a percent of the whole spectrum. Just the band from red to violet.
That's it.
That tiny sliver is the only part of electromagnetic reality that our biological hardware, our eyes, can actually process.
The notes bring up the concept of the rainbow here, which I think is a fantastic refresher.
Yeah.
Because a rainbow isn't an actual physical thing in the sky, right?
No, a rainbow is an event. It's essentially real-time spectral analysis.
How does that work?
The raindrops in the air act as tiny prisms. So white sunlight hits the water droplet and it gets bent, it refracts.
Okay.
But different colors within that white light have different frequencies. And because of that, they bend at slightly different angles inside the drop.
Wow.
Red is the lowest frequency of visible light, so it bends the least. That's why red always ends up on the outside arc of the rainbow. Violet is the highest frequency, so it bends the most, ending up on the inside.
So a rainbow is literally just a physical frequency chart displayed in the sky.
It's nature's PowerPoint presentation.
I love that. Now, once we go past violet, things change. We enter what feels like the danger zone. Ultraviolet, X-rays, gamma rays.
Why does the spectrum suddenly turn hostile to us here?
It is entirely about energy levels. Up until this point, radio, microwave, infrared, visible light, all those waves are what we call non-ionizing.
Non-ionizing.
Right, meaning they might heat you up like a microwave oven does, but they physically cannot change your atomic structure. They don't have the energy.
But the higher ones do.
Yes. Once you hit UV and above, the frequency is so insanely high that the photons actually act like tiny bullets.
So this is ionizing radiation.
Yes. They carry enough punch to physically knock electrons off your atoms.
And that damages your DNA.
Exactly. That is why UV light gives you a sunburn. It isn't heat, it is literally a radiation burn. It's why X-rays can see through you. They are so energetic they punch right through your soft tissue, but they get stopped by dense bone.
And gamma rays, the top of the spectrum. The extreme end. These are produced by nuclear explosions and black holes. They are incredibly destructive.
But the source material notes a beautiful twist of irony here.
We use them to cure cancer.
Right.
Through highly targeted gamma knife surgery, we can focus these waves to destroy deep brain tumors without a scalpel. We literally harness the destructive power of the wave to heal people.
It really highlights the unity of all this physics. It is all the exact same stuff, just photons traveling in waves.
Yeah.
Whether it is a pop song on the radio, the color blue, or a life-saving medical treatment.
It's all the same thing. The only difference is how fast it jiggles.
That is the beauty of physics right there.
Yeah.
One mechanism, infinite applications.
Truly.
Okay, so we have covered the how, which is modulation, and the where, the spectrum. Let's bring this home with the final pillar, The code.
The signal types.
Right. This is the grand battle between analog and digital.
And this is the shift that has completely defined the last 50 years of human technology.
So let's start with analog. The deep dive notes call this a continuous wave.
Continuous is the key word to remember. An analog signal mimics reality perfectly. It's entirely smooth.
Smooth.
Right, if you look at a sound wave of my voice right now, it ramps up and down in a smooth curve. An analog recording, like a vinyl record, cuts a physical groove into the plastic that follows that exact smooth shape.
You know, I've actually gotten back into vinyl recently, and there is something incredibly satisfying about just looking at the record under a light.
You can see the loud parts, right?
Yes, the grooves literally get wider and deeper. It is a physical map of the sound right there in front of you.
Exactly. And old landline telephones did the exact same thing, just with electricity.
How so?
Your voice vibrated a little diaphragm in the mouthpiece, which created a matching, continuous electrical wave that traveled down the wire. It's a direct, continuous copy of reality.
But the research points out a massive problem with making a direct copy. It copies absolutely everything, including the dirt.
That is the fatal flaw of analog noise. Yes. If you scratch that vinyl record, the needle reads the physical scratch just like it reads the music, so you get a pop.
Right.
If there is electrical static on the phone line, you cannot separate the static from the person's voice. The analog system does not know what is signal and what is noise. It just amplifies everything together.
And that is where digital steps in. The pulse.
Digital completely changes the philosophy of data. We basically stop trying to make a perfect, smooth copy of reality.
Okay.
Instead, we just sample the reality at tiny intervals and turn it into just two states, on or off.
1 or 0.
Yes, discrete steps instead of a smooth ramp.
Now, intuitively, when I read this, it felt wrong. In my head, a perfectly smooth line analog should clearly be higher quality than a jagged, blocky set of steps, digital.
It seems that way.
So why did digital completely take over the world?
Because digital is incredibly robust. It has a built-in immune system against noise.
How does that work?
Okay, let's say we are sending a digital 1, which we represent as a pulse of 5 volts of electricity, and a 0 is 0 volts.
Got it. 5 is 1, 0 is 0.
Now imagine some static interference comes in over the wire and messes with the signal. That 5-volt pulse drops down to 4.5 volts.
Okay, so in an analog system, that drop in voltage would literally change the sound coming out of the speaker. It would just be distortion.
Exactly, you'd hear the fuzz. But in a digital system, the computer chip on the receiving end looks at that pulse and says, well, 4.5 volts is basically 5 volts. It is definitely not 0.
Oh.
So I am just going to treat it as a perfect one.
It fixes it.
It regenerates the signal perfectly. It has a threshold, so it just filters out the mess.
That is brilliant. That is why a CD never crackles or pops no matter how many times you play it.
Exactly. And that concept slicing smooth reality into blocky binary code is the only reason we even have an internet today.
Because you can't email a vinyl record groove.
You can't. You have to turn it into math, into numbers first.
Okay, so if we pull all of this together, all 3 pillars, let's try to map the journey of a single everyday message to synthesize this whole deep dive.
Let's do it. Walk me through a scenario.
Okay, scenario. I am sitting in a local coffee shop.
Yeah.
I pull out my phone and I type, running 5 minutes late on WhatsApp to a friend across town. What just physically happened?
Okay, step 1, the code. Your phone takes the literal letters of that text message and converts them into a digital stream of binary. Thousands of microscopic ones and zeros.
Okay, step 2, the how.
Your phone's internal antenna takes that binary stream and uses QAM, that highly complex mix of phase and amplitude modulation we talked about, to basically imprint that binary code onto a carrier wave.
Step 3,
The where.
it blasts that modulated wave out into the room on a microwave frequency, likely 5 gigahertz if you're close to the router hitting the coffee shop's Wi-Fi.
And from the router.
The router converts it into infrared light pulses, shoots it down a glass fiber optic cable. It travels under the city streets at the speed of light, maybe bounces up to a cell tower near your friend, turns back into microwaves, and eventually reverses that entire process inside your friend's phone to show the letters. And that entire massive physical journey happens in what? 200 milliseconds?
Literally faster than the blink of an eye.
It really makes you feel a little ungrateful for complaining when a web page takes 3 seconds to load.
We are sitting around complaining about a literal miracle of engineering being slightly delayed.
We really are. Before we wrap this up today, looking at this huge stack of source material, is there one detail that fundamentally changes how you see the world?
For me, it always goes back to the AM radio waves bouncing off the ionosphere at
A
night.
skywave.
Yeah. There is just something remarkably elegant about it. Nature provided us with this global communication mirror in the sky, basically a free satellite dish made of plasma billions of years before humans even existed.
Wow.
We just had to figure out how to bounce a signal off of it.
That is beautiful. For me, it's the scale of perception. Just realizing that visible light, literally everything I've ever seen with my own eyes, every face, every sunset, is less than 1% of the reality that actually surrounds me.
That raises a really fascinating question to leave everyone listening with.
Let's hear it.
If we are constantly, 24/7, bathed in these invisible rivers of data, GPS timing signals, background radiation, radio waves, Wi-Fi streams, and our biological senses cannot perceive any of it without machines, are we really seeing the world?
Or are we just seeing the user interface?
Exactly. We are just clicking the pretty icons on the desktop, totally unaware of the massive operating system running underneath.
That is slightly terrifying, but mostly it is just awesome to think about.
It really is.
So to everyone listening, the next time you point your infrared remote at the TV or you lose your favorite FM radio station behind a big hill, just take a second to remember you are physically interacting with the invisible highway of the universe. Thank you for joining us on this deep dive.
See you next time.
I want you to picture something I guarantee you have done 1,000 times.
I'm sure.
You wake up, you stumble into the bathroom,
Right.
you turn on that really harsh overhead light, and you look in the mirror.
Right.
You see your face.
Yeah.
And maybe you're checking a blemish or, maybe you're just brushing your teeth. But it feels like the most concrete, undeniable reality in the world. You are there, and that reflection is you. But here's the question that honestly kept me up last night while I was prepping for this deep dive. Is that reflection actually real? Or is it a hallucination that your brain is constructing because it's just too stubborn to understand physics?
That is a hell of an opener. But you're not wrong.
Right.
We tend to think of our eyes as these perfect little cameras that just passively record the world, but they aren't. They are interpreters, and frankly, they take a lot of creative liberties.
They really do. And that is exactly our mission for today. We are diving back into our series on communication, waves, and optics, but specifically, we're looking at light today.
Yeah.
Not just the particles and waves, but the grand illusion that they create for us.
It's such a great topic because it bridges that gap between hard, cold physics, geometric rules, angles, the math, and the squishy biological reality of how we actually experience life.
Yeah.
We're going to unpack the source material on reflection, which is bouncing, refraction, which is bending, and perception, which is our actual biological hardware.
And the overarching theme I keep getting from all these sources is basically your brain is an unreliable narrator.
It absolutely is. And honestly, it has to be. I mean, if we process every single photon exactly as it entered our eyes without any shortcuts, we would probably crash.
Right, like a computer running out of RAM.
Exactly. We need those shortcuts to survive. But understanding how those shortcuts work, that is where the physics comes in.
So let's start with the bounce. Reflection. The basic premise here seems simple enough. I throw a tennis ball at a wall, it bounces back. Light hits a mirror, it bounces back.
Essentially, yes. And this is governed by the law of reflection. It's arguably the oldest law in optics. It simply states that the angle of incidence, the incoming angle equals the angle of reflection. Angle I equals angle R.
So if I shine a laser pointer at a mirror at a 45-degree angle, it leaves at a 45-degree angle.
Spot on. It is perfectly symmetrical. And we see this in the mirror hand trick that the notes mention.
Oh yeah, I love this one.
You stand in front of mirror, you raise your right hand. The reflection raises what looks to be its left hand. It's a direct consequence of that light bouncing straight back at you symmetrically.
But the sources point out something that I hadn't really connected before. This isn't just about bathroom mirrors. This is the exact same math that keeps airplanes from crashing into each other.
Radar. It is the exact same principle, just a different wavelength.
Right.
An air traffic control tower isn't shining a flashlight into the sky, obviously. They are firing pulses of radio waves.
And those waves hit the plane.
They hit the metal skin of a Boeing 747. They bounce off, obeying that exact law of reflection, and they return to the radar dish.
And since we know the speed of light is constant, the time it takes for that signal to bounce back tells us exactly how far away the plane is.
And the angle tells us the elevation. It's incredibly simple geometry, but it's saving millions of lives a year.
Okay, but let's go back to the bathroom mirror for a second, because this is where that hallucination part comes in. The notes talk about a plane mirror, which is just a standard flat mirror, and this concept of a virtual image.
Yes.
Now, normally the word virtual implies computer-generated, right?
Yeah.
But this concept is way older than computers.
Much older. Think about what happens when you look at your reflection. You see yourself standing about 2 feet behind the glass, right?
Yeah. It looks like there's a whole other room back there, behind the mirror.
But you know there isn't. There's a wall there. Or a medicine cabinet. Light cannot pass through the mirror. It bounces off. So why do you see a face behind the glass?
I always just assumed it was, well, I don't really know, a
Mm.
trick.
It is your brain being incredibly stubborn.
Mhm.
Your brain evolved under one strict, unshakable rule. Light travels in straight lines.
Right.
It inherently assumes that if a light ray enters your eye, it must have come from a straight line directly in front of you.
So it refuses to acknowledge the bounce.
It completely ignores the bounce. So when light bounces off the mirror and hits your eye, your brain goes, well, light travels straight, so I'm going to trace this ray backward through the mirror, through the wall, to where the object would be if the light hadn't bounced.
Oh, wow. So it's drawing a dotted line through solid matter and creating a phantom object just to satisfy its own internal logic.
That is exactly what a virtual image is. It is a mental construction. It's an image that cannot be projected onto a screen because the light isn't actually physically there.
Because the light bounced.
Exactly. It exists entirely because your brain is auto-correcting reality to fit that straight line rule.
That is just profound to me. I'm staring at a mental projection every single morning. But mirrors aren't always flat, are they? We have the curvy ones, too.
We do. And once you curve the surface, you really start hacking the law of reflection. First, you have concave mirrors. Think of a cave curving inward.
Oh, these are the ones that are terrifying to look into if you have pores.
Yeah.
The makeup mirrors?
The vanity mirrors, yes. A concave mirror is a converger. It takes parallel rays of light and forces them all to meet at a single focal point.
Okay.
If you put your face inside that focal point, the geometry stretches the image. It magnifies it.
Which is great for shaving or applying eyeliner, but completely humbling for your self-esteem.
Definitely.
But the notes say this shape isn't just for vanity. It's actually used for power.
Right. Think about satellite dishes. They are just giant concave mirrors for radio waves. They catch a really weak signal from space that's spread out over a wide area, and they focus all of it onto that one tiny receiver in the middle.
Or car headlights, but working in reverse, right?
Exactly.
You put the bulb in the middle of the focal point, and the mirror takes that scattered light and shoots it out in a focused beam down the road.
Precisely. It is all about controlling the direction of energy. Now, if you take that curve and flip it the other way, you get a convex mirror. It bulges outward.
Like the back of a spoon. Or those big dome mirrors in the corner of a convenience store.
Right. A convex mirror is a diverger. It takes incoming light rays and scatters them outward. Now, why would you want to do that?
Well, if I'm looking at one of those mirrors in a tight parking garage, I'm trying to see around a blind corner. I need to see a really wide area.
Exactly. Because the surface curves outward, it catches light from a much wider angle. It pulls in light from the sides, from the ceiling, from the floor, and bounces all of it toward your eye. It gives you a massive field of view.
But there's a cost.
There is always a cost in physics. To fit that massive panoramic view into a small mirror, the image has to be squashed. Everything looks smaller.
Objects in mirror are closer than they appear.
Yes. That warning on your car's wing mirror is literally a physics disclaimer. It's telling you we distorted reality to give you a wider view, so do not trust your depth perception here.
Once again, the unreliable narrator strikes. Okay, so that is reflection. Bouncing. Now we move to the phenomenon that I think trips people up even more. Refraction. The art of the bend.
This is where we leave the mirror and we enter the lens. Refraction happens when light travels from one medium into another, like from air into water or air into glass.
And the mechanism here is speed, right?
Yes. Light has a top speed, the speed of light in a vacuum, but when it hits something dense like water or glass, it has to slog through all those molecules, so it slows down.
Okay.
And if it hits that new medium at an angle, one side of the light wave slows down before the other side does.
The classic analogy in the sources for this is the shopping cart, isn't it? If you push a shopping cart from smooth pavement onto thick grass at an angle,
the wheel that hits the grass first slows down. That acts like a pivot point, and the whole cart turns. That is exactly what light does. It changes direction because it changes speed.
and we see this every time we put a straw in a glass of water, it looks broken.
But the straw is fine. The light coming from the straw is bending as it leaves the water and hits the air. And remember, Our stubborn brain.
Oh, right. It still thinks light travels in perfectly straight lines.
So it traces that bent light back in a straight line, which creates a virtual image of the straw that is shifted completely sideways.
This brings up the fishing problem. I mentioned in the intro the idea of trying to grab a fish in a pond and missing.
Yeah.
The notes actually call this a classic refraction trap.
It really is. If you are standing on a riverbank looking down at a fish, the light reflecting off that fish travels up through the water, hits the boundary of the air, speeds up, and bends down toward your eye.
Okay, let me visualize this. Light bends down, so the angle becomes shallower.
It bends away from the vertical, yes, but your brain traces it back along that new steep angle. So to you, the fish looks like it is floating much higher, much closer to the surface than it actually is.
So if I aim my spear, or even just my hand, directly at the fish I see, I'm just going to splash water. Because the real fish is deeper.
You have to aim low to hit the mark. You have to intellectually override the visual data your brain is feeding you.
Yeah.
You literally have to outsmart Snell's law.
Snell's law. That's the math for this.
It is. It's the formula that relates the angles and the speeds between two mediums. But unless you are calculating lens curvature, you don't really need to memorize the formula. What matters is the application.
Right.
And the biggest application is sitting on the noses of billions of people right now. Glasses.
Lenses. A lens is basically just a controlled refraction device.
That is a brilliant way to put it. We use glass to bend light, specifically to correct the biological errors in our own natural lenses.
The notes mention dioptries here. I've seen that on my glasses prescription. Minus 2.5 plus 1. I honestly always just thought of it as a badness scale. Like, the higher the number, the worse my eyes are.
That's certainly one practical way to view it. But physics-wise, think of dioptries as a measure of optical power, or maybe aggression.
Aggression.
Yeah. How aggressively does this lens bend light? A lens with a power of +1 dioptry is very gentle. It takes parallel light rays and slowly bends them so they meet a full meter away. It's a subtle nudge.
Okay. So what about a plus 10?
That's a magnifying glass. That is
Okay.
aggressive. It grabs the light and forces it to converge in just 10 centimeters. It's a powerful bend. The math is simply power equals 1 divided by the focal length.
So if I am short-sighted, which I actually am, I have a negative number on my prescription.
Right. Short-sighted means your eye's natural flexible lens is actually too aggressive. It focuses the image before it even hits your retina at the back of your eye.
Oh, I see.
So you need a concave lens, a diverger, to spread the light out a little bit before it enters your eye, basically canceling out your eye's over-enthusiasm. That is why your prescription has a minus sign. It is literally subtracting power.
That makes so much sense. I am wearing anti-power glasses.
Mm-hmm.
Now, there's one more refraction concept here that feels like pure magic, but it's really just extreme physics. Total internal reflection.
This is the backbone of the modern world. We talked about light bending when it leaves water or glass, but if the light hits that boundary at a really steep angle, what we call the critical angle, it can't get out.
It gets stuck.
It tries to bend so much that it actually bends back into the material.
So it gets completely trapped inside.
Exactly. Imagine skipping a stone on a calm lake. If you throw the stone straight down, plunk, it goes into the water. That is normal refraction. But if you throw it at a really shallow angle, it bounces off the surface and skips along.
Okay, I'm with you.
Total internal reflection is basically skipping a photon of light along the inside of a glass tube. It bounces off the internal walls over and over again, zigzagging its way down the cable at the speed of light.
And this is fiber optics.
This is the entire internet. When you send an email or stream a video, it is being converted into pulses of light that skip stone their way from New York to London through a hair-thin strand of glass without ever leaking out.
It is wild to think that the entire global economy rests on trapped light skipping down a tiny glass tube.
It's efficient, it's incredibly fast, and it's secure. And it's the exact same tech that surgeons use with fiber optic endoscopes to see inside your stomach without cutting you open. They were just piping light around corners using internal reflection.
Okay, so we have covered the signal transport. We've got mirrors bouncing the light, lenses bending it, cables trapping it. But now we have to talk about the destination. Part 3, the receiver.
Right.
Because all this light bouncing around is completely useless if we don't have a biological way to interpret it.
And this is where the unreliable narrator theme really kicks into high gear. We tend to trust our senses implicitly, but the sources emphasize just how incredibly limited they actually are.
The notes start with vision, obviously. It says sight accounts for roughly 80% of all our perception. We are deeply visual creatures.
We are. The retina, which is the screen at the back of the eye, is a marvel. It has these specialized photoreceptors called rods and cones, but they work in very different ways.
Cones are for color and fine detail, right? Like high-definition cameras.
Yes, but they are divas. They need a lot of light to work. If it gets dim, they just clock out. That is when the rods take over.
Okay.
Rods are incredibly sensitive. They can detect a single photon of light, but they are low resolution, and crucially, they are colorblind.
Wait, so when I turn off the lights in my house and everything looks gray and shadowy,
It's not that the objects lost their physical color, it's that your brain switched inputs. You are literally seeing in black and white because your color hardware went offline.
so color isn't an intrinsic fixed property of the object itself. It's a construction of the specific cells that happen to be firing in my eye at that exact moment.
Exactly. We can distinguish about 10 million colors, but only when the lighting is right. And if we move to hearing, it's even more restrictive. Hearing is purely mechanical. It's not electromagnetic waves like light. It is physical air pressure pushing on your eardrum.
Which vibrates those tiny bones, the ossicles, and then sends a signal through the cochlea to the brain.
But the hardware has strict physical limits. Humans can hear frequencies from about 20 hertz up to 20,000 hertz. That is our entire window.
But the world makes sounds outside that window.
All the time. A dog's hearing goes up to 65,000 hertz. So a dog whistle sits at around 30,000 hertz. To you, blowing that whistle is a completely silent act.
But to a dog, it's a blaring siren.
The sound is objectively there, the air is physically vibrating. But your reality simply does not include it because you lack the biological tuner to pick it up.
It really makes you wonder how much of the universe is just happening right in front of us, but we are just tuned out.
Probably most of it. We perceive a tiny slice of the electromagnetic spectrum and a tiny slice of the acoustic spectrum. We are walking around looking through a keyhole and calling it the whole world.
And then there's the chemical senses. Touch, taste, and smell. The notes bring up something here that I think everyone has experienced but maybe didn't understand the actual mechanism of. Flavor physics.
The great lie of the culinary world. We think we taste food. But biologically speaking, your tongue is a very blunt instrument. It can only detect sweet, sour, salty, bitter, and umami. That is it.
So where does strawberry or chocolate or smoked salmon come from?
That is all smell. It is a process called retronasal olfaction. Aromas travel from the back of your mouth up into your nasal cavity. Your brain combines the simple signal from the tongue, like sweet, with the highly complex signal from the nose, like strawberry, and synthesizes a completely new flavor experience.
Oh, this explains why food tastes like wet cardboard when you have a cold.
Exactly. If your nose is blocked, you cut off the main data stream. You still get the physical texture and the basic sweetness from the tongue, but the strawberry definition is entirely gone. The flavor literally doesn't exist without the smell. It also explains why smells trigger memory so strongly.
Because it's a chemical sense linked straight to the brain.
Yes, the olfactory bulb has direct neural connections to the amygdala and hippocampus, which handle emotion and memory. It's an ancient survival mechanism that lets a scent instantly transport you back in time.
So let's recap this whole journey, because when you stack it all up, it is kind of disorienting.
It really is.
We started with reflection. We learned that when we look at a mirror, we aren't seeing direct reality. We are seeing a virtual image constructed by a brain that simply refuses to understand angles.
Then we looked at refraction. We learned that the position of a fish in water or a broken straw is a projection, not a coordinate. We learned that we have to strap curved glass onto our faces to warp reality just to get it to focus properly on our retinas.
And finally, perception. We learned that color is a sometimes feature that turns off in the dark, that sound exists loudly even when we can't hear it, and that the rich taste of our dinner is largely a smell that our brain decides to credit to our mouth.
When you put it that way, calling the brain an unreliable narrator is putting it mildly, but it's highly relevant. Every time you check your blind spot in a car mirror or put in your contacts or stream a video over fiber optics, you are actively utilizing these exact laws of physics.
It really forces you to ask, what is actually real?
And that is the deeper, more provocative lesson of physics here. Physics isn't just about measuring the external world. It is about measuring the limits of our interaction with the world. The virtual image isn't just a term for mirrors. In a very real way, your entire conscious experience is a virtual image.
Wow.
It's a mental model built by your brain using data that has been bounced, bent, filtered, and heavily compressed long before it ever reaches your conscious mind.
So we basically are living in a simulation, But the computer running it is just the gray matter inside our own skulls.
Pretty much. We never see the world exactly as it is. We only ever see the brain's best guess.
Well, I don't know about you, but I am going to have a very hard time trusting my bathroom mirror tomorrow morning.
Just remember, it is not the mirror lying to you. It is you lying to you.
Huh. Thanks for that comforting thought.
Yeah.
And thank you to everyone listening to this deep dive. We will catch you in the next one, assuming you can still trust your ears.
Welcome back to the deep dive. I want to start today by just throwing a number at you. A number that actually made me put my coffee down when I was reading through the source material.
Oh, I know the one.
Yeah, you know exactly what I'm talking about. So if you sit down to watch a single hour of 4K video, like just one episode of whatever series you're binging right now, the device in your pocket or on your desk has to process 400 billion ones and zeros.
400 billion. And that's honestly a conservative estimate.
Right. It's a number so big it almost, well, it stops meaning anything. It's just noise.
Mm-hmm.
But our mission today is to turn that noise back into signal. We're diving into part 3 of our sources, specifically the section on technology and society. And we're going to attempt something kind of crazy today.
Here you are.
We want to trace the journey of a single piece of information. From the literal subatomic physics that makes it possible, through the cable sitting at the bottom of the ocean, all the way to the psychological tricks that keep us, doom scrolling at 2 a.m.
It's the ultimate journey from the micro to the macro. And, we so often talk about technology like it's just magic.
Totally.
You tap a piece of glass, a car shows up at your door, you speak to a little cylinder on your counter, it plays your favorite music. But my goal today is to really strip away that magic label. Because when you actually understand the mechanisms, the physics, the engineering behind it, it is far more impressive than magic.
I am so ready to have the illusion shattered. But let's be real. For most of us, the mechanism is just a complete black box.
Yeah.
We know computers speak binary. We know it's all ones and zeros. But I feel like most people just stop there. They don't really know why it has to be ones and zeros.
Right. Like, why not 1s, 0s, and 2s?
Exactly. Why limit it to just 2 options?
It really comes down to one thing: reliability.
Yeah.
It is incredibly difficult to build a physical machine that can perfectly distinguish between, say, 10 different voltage levels.
Like 0 through 9.
Right, 0 through 9. Doing that billions of times a second without ever making a mistake. Nearly impossible. But distinguishing between current is on and current is off.
That's much easier.
Exactly. That is robust. It's physically unambiguous.
So it's sort of the difference between trying to whisper a very specific volume level across a crowded, noisy room versus just, I don't know, flashing a really bright flashlight on and off.
That is a perfect analogy,
You got
yes. So at the absolute bottom of the stack, you have the bit, a 0 or a 1. And as you mentioned, everything's just a sequence of these. Take the letter A.
Okay.
It's not an actual A floating around inside the machine. It is stored as ASCII codes 65,
Right.
which in binary translates to 01000001.
So whether it's Shakespeare or cat video or, even a little computer running my microwave,
Yes, your microwave too.
it's all just that same alphabet of 2 letters.
Precisely. But here's where we need to push a bit deeper than the usual textbook explanation. A stream of 1s and 0s. That's just data. It's not computing. To actually compute, to make a decision, you need a physical structure that can manipulate those 1s and 0s.
Enter the transistor.
Yeah.
The heavy lifter of the whole operation.
The engine of the modern world.
Yeah.
A transistor is, in its absolute simplest form, just a switch. But it's not a mechanical switch like the one on your wall.
It doesn't physically flip.
Right. It's a semiconductor switch. It uses the properties of silicon, specifically silicon, that's been doped with other elements to control the flow of electrons without moving parts.
And this is where the actual logic comes in, right? Because a single switch turning on and off is pretty boring. But if you start connecting them...
Now you're thinking like an engineer.
Hmm.
If you wire 2 transistors together in a series, you create what's called an A and D gate.
Okay.
The current only flows through if switch A and D switch B are both on.
Got it. So that's the literal physical manifestation of logic. Like, if this condition is true and that condition is true, then proceed.
Exactly. And if you wire them in parallel instead, you get an OR gate. If switch A or switch B is on, let the current through.
It's so simple.
Very simple. But when you combine millions of these AND or R and NOT gates, You can build a circuit that does math. You build a circuit that can remember things. You build a circuit that can run a massive 3D simulation.
It's just layers of incredibly simple logic stacked up into mind-boggling complexity.
Yeah.
But the physical scale of this is what absolutely breaks my brain. The source material mentioned the first transistor back in 1947. That was, what, roughly the size of a golf ball?
It was a clunky, palm-sized, hand-built device.
Yes.
And today, we are talking about components that are just a few nanometers wide.
The comparison in the text, I actually had to double-check this because I didn't believe it. It said a modern transistor is smaller than a virus.
Much smaller. A typical virus might be about 100 nanometers across. We are currently mass-producing transistors at the 3 nanometer and 2 nanometer scale.
Wow.
You can fit literally over 10 billion of them on a processor chip roughly the size of your fingernail.
That density is just terrifying. And honestly, it explains why my laptop gets so hot when I'm working. You've got billions of tiny switches flipping on and off billions of times a second. That friction, or that energy, creates heat.
Yeah, that density is basically the defining story of the last 50 years of human history. It's Moore's law.
Gordon Moore, 1965.
Right. He observed that the computing power, the density of these transistors, was doubling approximately every 2 years, while the cost halved.
Which has held up remarkably well. I mean, think about the computer that took the Apollo 11 astronauts to the moon versus what we literally carry in our pockets every day.
It's not even a fair comparison anymore. The Apollo guidance computer was a brilliant piece of engineering, but it had less raw processing power than a modern musical greeting card.
That is wild.
Your smartphone is vastly more powerful than all the computing capacity of NASA combined in the 1960s.
So we are essentially using a global supercomputer network to, look at memes.
Effectively, yes.
Yeah.
But there's a catch we're running into now. We are finally hitting the physical limit. When you get down to 2 or 3 nanometers, you are dealing with individual atoms. And at that scale, quantum mechanics starts to mess things up. Electrons can literally just tunnel through the closed switches, even when they're supposed to be off.
Oh, because the barrier is so thin? So Moore's law might be ending soon, not because we aren't smart enough to keep going, but because the actual laws of physics are stepping in and saying stop.
We're definitely bumping hard against the ceiling. But let's zoom out for a second. We've got this incredible supercomputer in our pocket. But a computer sitting by itself is basically just a very expensive rock that can do math.
Right. It's totally useless without connection.
The network.
Yeah.
We need to be able to move those billions of zeros and ones from your pocket to, say, a server in Japan, and then get an answer back.
Which brings us to the actual infrastructure of the internet. I think most people just have this vague floating idea of the cloud, but the cloud is really just someone else's computer connected to yours by a very long wire.
A very long, extremely expensive physical wire. Let's actually trace a request. Say you click a link to a website hosted in Japan. Your phone turns that click into a radio signal, your home Wi-Fi, or maybe 5G, which then hits your router or a local cell tower.
Right, that's the local area network, the LAN.
Exactly, that's the easy part. But then it leaves your local bubble. It enters the wide area network, the WAN. And this is where the real genius of the internet comes in packet switching.
Okay, unpack that term for us. Because I remember hearing way back that the internet was originally designed to survive a nuclear war.
That was the original concept for ARPANET, yeah.
Yeah.
Think about the old telephone days. If you called someone across the country, a literal physical circuit of copper wire was opened up between your phone and theirs.
A dedicated lane just for us.
Exactly.
Yeah.
But if a storm knocked down a telephone pole in the middle of that route, the call died. The line was dead.
Right.
The internet does not do that. It takes your data, say an email or an image, and chops it up into thousands of tiny digital pieces called packets. Each packet is basically a digital postcard. It has the address of where it's going, the IP address, and a little sequence number saying, hey, I'm packet 4 out of 100.
And the network just sort of throws them into the wind.
Sort of. It throws them into the network. And the beauty of the TCP/IP protocol, the language of the internet, is that each packet can take a completely different route to get to Japan.
Oh, I see.
Packet 1 might go through routers in Paris. Packet 2 might bounce through London. If a cable gets cut in Paris, the routers instantly notice and just divert all the remaining packets through London instead.
And then your computer at the very end in Japan catches all these scattered, out-of-order postcards and just reassembles them perfectly based on those numbers.
Instantly. It looks chaotic, but it is incredibly resilient. And every device on this network needs a unique address, an IP address. But because humans are terrible at remembering long strings of numbers.
We use the domain name system, DNS.
Yes. DNS Acts like the internet's phone book. You
Mhm.
type in google.com, and DNS silently translates that into the actual IP address, something like 195.88.54.1, so the routers know where to send your packets.
It's brilliant. But these packets still have to physically travel over something. And for these massive global distances, we aren't using copper telephone wires anymore. We're using light.
Fiber optics. This is the true backbone of the internet. We are literally shooting lasers through threads of glass that are thinner than a human hair.
Now, I have a physics question here. If I shine a flashlight into a regular glass tube, the light just sort of shines out the sides, right? How does the data stay trapped inside the cable for 3,000 miles under the freezing ocean?
It relies on a physics phenomenon called total internal reflection. The glass core of the fiber is wrapped in a different layer of glass called cladding. If you shoot the laser at a shallow enough angle, the boundary between those two layers acts like a perfect, flawless mirror.
So it just bounces.
Right, the light bounces in a zigzag pattern all the way down the line with almost zero loss.
Traveling at the speed of light.
Well, about two-thirds the speed of light in a vacuum, because light moves a bit slower when it's traveling through glass. But yes, incredibly fast. A single strand can carry thousands of simultaneous phone calls or video streams.
I always find it kind of funny that we think of the internet today as completely wireless, but wireless is really just the last 50 feet from the router to your phone. Everything else is these huge, heavy cables lying on the bottom of the ocean, stretching from Norway to the USA, occasionally getting bitten by sharks.
They actually do have to heavily armor those submarine cables against shark bites and deep-sea trawler nets. It is a very fragile physical reality holding up our entire digital world.
And even that last wireless jump is getting insanely fast. The source mentioned mobile networks and 5G speeds.
Yeah, cellular networks divide cities into geographic cells, each with a base station. As you drive, your phone constantly negotiates with the towers, handing off the signal seamlessly.
Right.
And with 5G, using Oslo as an example from the text, you can see download speeds over 1 gigabit per second.
Which means downloading a full HD film in a matter of seconds.
Exactly.
So, okay, we have the microscopic silicon brain, and we have this global fiber optic nervous system. But it's crazy to think none of this existed roughly 150 years ago. And the story of how we got here is, well, it's pretty ironic.
It really is. To understand it, we have to talk about the pioneers. Specifically, two giants of history, James Clerk Maxwell and Heinrich Hertz.
Maxwell is the theoretical guy, right? Like the Einstein of the 19th century.
Funny you say that. Einstein actually kept a framed portrait of Maxwell on his study wall.
Oh, wow.
That is how important he was. In the 1860s, Maxwell looked at electricity and magnetism, which scientists at the time thought were completely separate phenomena. And he used pure mathematics to prove there were actually two sides of the same coin, electromagnetism.
And his math predicted that this unified force traveled in waves.
Yes. He basically said the math dictates that these invisible waves of energy must exist in the air around us. But he died 20 years before anyone could actually find them.
Enter Heinrich Hertz, the hands-on experimentalist.
Exactly. Fast forward to 1887. Hertz builds a contraption in his lab, a spark gap transmitter. Basically, he creates a high-voltage spark between two brass balls. And across the room, with absolutely no wires connecting them, a second little receiver loop sparks at the exact same moment.
That is the massive aha moment. He sent energy through the air. He proved Maxwell's radio waves were real.
He proved the invisible was tangible. But here is the irony you hinted at. When people asked him, Heinrich, this is amazing. What are we going to use this for?
I absolutely love this quote. He didn't say, oh, we're going to build a global communication network.
Well, he famously replied, it's of no use whatsoever. It's just an experiment that proves Maestro Maxwell was right.
Of no use whatsoever. The literal foundation of Wi-Fi, GPS, radar, television, your 5G mobile phone, and the guy who proved it existed thought it was just a neat parlor trick for physicists.
It is the ultimate reminder that basic fundamental research doesn't always have an immediate, profitable product attached to it. You often don't know what you found until decades later. Fortunately, inventors like Morse with the telegraph, Bell with the telephone, Marconi sending signals across the Atlantic, and Tesla with AC power, they came along and realized, hey, maybe we can use these useless waves to change the world.
And that leads us directly to the present day. We took those waves, we saturated the air with them, we built these massive globe-spanning networks. But now we actually have to deal with the fallout, because living in this digital ocean isn't without some pretty heavy consequences.
This is the critical shift in the source material toward digital citizenship. We have built the matrix, and now we actually have to live inside it. And the very first thing we need to acknowledge as citizens is the business model powering it all.
The myth of the free internet.
Right. We use search engines, social media, video platforms. We don't pay a monthly subscription for most of them. But those massive server farms cost billions to run. The underwater fiber cables cost billions to lay.
Yeah.
So who is paying the bill?
The advertisers, which naturally means we are the merchandise.
We are the resource being mined. Our attention and our behavioral data. Every time you click a link, every time your mouse hovers over an image, or you pause your scrolling for 2 seconds on a specific video, that is a data point.
It's all fracked.
All of it.
Yeah.
It's harvested to build a psychological profile of you that is, in many cases, likely more accurate than your own self-perception.
You know, it's fascinating how this ties directly back to the network architecture we were just talking about. The original internet was built to move those packets efficiently and resiliently. It wasn't necessarily built to move them securely or privately. It was built for academic sharing.
Exactly. The early ARPANET relied on absolute trust between a few universities. It was simply not designed for a globalized world where your identity or bank details could be stolen by an automated bot sitting in a completely different hemisphere. And that is exactly why we are constantly patching the system with new security measures.
Which brings us to the eat your vegetables part of the deep dive, security hygiene.
It's vital, though. Take encryption. We mentioned those digital postcards earlier, the packets. Without encryption, anyone sitting on a router anywhere between you and Japan can just read the postcard as it flies by.
Just like a shady mail carrier reading your physical mail.
Exactly. Encryption takes that postcard and locks it inside a titanium briefcase before it leaves your device. That is what end-to-end encryption on apps like WhatsApp does. That is what the HTTPS and the little padlock icon in your browser mean.
So even if someone intercepts the data packet, it's completely unreadable.
Right. Unless they have the specific cryptographic key, all they see is random garbage noise.
And then there is authentication.
Passwords alone are effectively dead. They're far too easy for computers to guess or for phishing scams to steal. You have to use two-factor authentication, or 2FA. It combines something you know, like your password, with something you physically have, like a code sent to your phone.
I have to admit, I used to find 2FA incredibly annoying. But now, visualizing my little data packets bouncing through random servers in Paris or London,
Yeah.
I want the locked titanium briefcase, and I want the extra padlock.
You definitely do. But there is a totally different kind of threat that encryption cannot protect you from. And that is the threat to our own psychology, the digital well-being aspect.
Honestly, this is the stuff that scares me way more than the hackers and hoodies. The idea that the device isn't just vulnerable to being hacked, but that it's actively designed to hack me.
It is engineered addiction. We have to be brutally honest about that. The UI designers of these major apps use the exact same psychological principles as casino slot machines.
The source material specifically highlighted the variable reward schedule.
Precisely. Think about it. If you pulled a slot machine lever and a little piece of candy came out every single time, you'd get bored in 5 minutes.
Right.
But if you pull the lever and sometimes you get a candy, sometimes you get absolutely nothing, and sometimes you hit a massive jackpot of coins, your brain releases dopamine. You will sit there and pull that lever until you physically pass out.
And that is the exact psychology behind the pull to refresh mechanism on our feeds.
It is a literal slot machine lever. You swipe down and you have no idea what you're going to get. Will it be a life-changing news update? A funny meme? Or nothing at all? That uncertainty is incredibly addictive.
And to make it worse, they removed all the natural stopping cues.
The infinite scroll. That was a very deliberate, calculated design choice. In the analog world, the newspaper physically ends. A television episode has credits. There's a built-in cue to stop, breathe, and decide what to do next. But an algorithmic feed never ends. It removes that crucial decision point of asking yourself, should I continue?
And the result of all this engineering is that the average person is checking their phone, what was the stat, 96 times a day?
Roughly 96 times a day, yes. That averages out to once every 10 or 12 minutes of your waking life. It completely fragments our attention spans. It creates this constant low-level background radiation of anxiety and FOMO, the fear of missing out.
There's a huge debate happening around this right now, especially concerning education. The source material notes that countries like Norway are looking at this very closely.
The research data is coming in, and it's pretty damning. Policies that remove smartphones from classrooms tend to result in noticeable spikes in student concentration levels and overall test scores. And we need to be clear, it's not because kids today are bad or lazy, it's because the device in their pocket is a super stimulus.
It's literally engineered by thousands of the smartest people on Earth to be more interesting than whatever the algebra teacher is saying.
Exactly. It's doing exactly what it was designed to do.
On that note, there's also the legal pushback against all this data harvesting. The GDPR in Europe, which the text mentions, affects Norway directly. It's giving people rights to access their data or demand it be deleted.
Yes, the right to be forgotten. It's a vital step. It shifts the power balance slightly back toward the user.
So we've unpacked the microscopic transistors, the submarine fiber optics, the history, the psychology, the legislation. It's a lot to process. But I guess the ultimate question for the listener is, what do we do with all this? Because we can't exactly just throw our laptops in the ocean and go live in the woods.
No, and we really shouldn't want to. This technology gives us practically godlike powers of global communication and access to the sum of human knowledge. The key to being a responsible digital citizen is simply awareness.
It's looking at the piece of glass in your hand and seeing the billions of transistors instead of just seeing magic.
Right. When you understand how the magic trick is actually performed, you are far less likely to be fooled by it. When you recognize that pull to refresh is a casino mechanic, it loses a little bit of its psychological grip on you. When you truly understand that free means data mining, you start making much better choices about what you share online.
It's about taking back a little bit of agency in a system designed to strip it away.
Exactly. We are supposed to be the pilots of this technology, not the passengers. Or at least, we need to try to be.
I love that. But before we wrap up, I want to circle all the way back to Heinrich Hertz to close this out, because I genuinely cannot get over that useless comment.
It haunts you, doesn't it?
It really does, because it immediately makes me wonder, what are we looking at right now today that we are completely dismissing? What is the weird, seemingly useless little scientific anomaly that some grad student is playing with in a basement lab right now thinking, oh, this is just a neat physics trick, but in 100 years it's going to be the foundation of a completely new human civilization?
That is the ultimate question.
Yeah.
The next radio wave is definitely out there. We just have to be open-minded enough to recognize it, even if it looks totally useless today.
Well, I'm going to go stare at my Wi-Fi router for a while and think about sharks biting the internet. Thank you so much for taking the deep dive with us today.
Always a pleasure.
See you next time.